So working at 헬라2 in the specific entity developing all our portfolio of sensors, as you can see on the left side, and working on automated vehicles, the topic of the session rings a bell, and a pretty loud one to tell you the truth. It is one of the main challenges we have. How can we guarantee an availability of the ADAS functions of high automated level in all weather conditions, through rain, fog, snow, low sun, etc., during day and during night? Is there one technology better than the other and that checks all the requirements? High resolution, good contrast, precise distance evaluation of any classified object, person, mobility device, lane marking? What is the impact and the influence of the public road lighting, or even the light coming from the other road users? So our speakers today are going to share with us their researched and clever point of view on these questions. There will be an overview of emerging new technologies, a study on the interaction of automotive sensors and road lighting, as well as a pinpoint of the influence of glare from oncoming vehicles on the object detection. So enjoy this session. Our first speaker is going to be Simon. PhD researcher at 헬라 in cooperation with the Technical University of Berlin, and he has asked himself the following question: can a conventional camera be tuned to measure the road surface luminance? And here is his answer.
Yeah, thank you very much for the kind introduction, and welcome to my presentation with the title Detection of Road Lighting Using a Conventional Camera System. My name is Simon Vogel. I'm a PhD student at the hella, which is the research department of hella2 in cooperation with the Technical University of Berlin. And my research topic investigates and discusses the combination of automotive headlamps and road lighting. And from a car's perspective, how we can adapt to the given road lighting situation. This is also where today's topic is connected to. However, I would like to start with a little bit brighter motivation, such as you can see why there is so much potential in this field. For that, I would like to show you this luminance measurement taken from the perspective of a driver, and it shows you a road which is illuminated on the one hand by the automotive headlamp. You can see that by the bright area in yellow in front of the car where the pre-filled module is working, and it's also on the other hand illuminated by the road lighting. You can see the road luminaires. You can also see that there's a rather uniform luminance on the road, even in distances rather far away from the car. And you might already see that there's something on the road, so let's zoom in and investigate what is there. And there we see two different square targets in the middle of the road, which are revealed to us by a positive contrast. That means that they appear brighter in front of a darker background, and this is what automotive lighting excels in. It's very good at creating high object luminances to things perpendicular to the road surface, such as those cardboards here. However, it's not so good at illuminating the road surface itself due to its angle. It's illuminating the surface. So typically when we only have road lighting, things are revealed to us by a positive contrast. So now it says headlamp on plus road lighting. What happens now when we turn the headlamp off? Out of nowhere we suddenly see a third target appearing on the very right of the two previous ones, which is now revealed to us by negative contrast, because this is what road lighting is very good at. It can create high road surface luminances due to its perpendicular illumination of it, and also in distances very far away where our headlamp is not so good at. However, it's not so good at creating high object luminances. As a result, we only see a negative contrast. And this is now a different thing to notice, because when we have headlamp on plus road lighting, we do not see the third target. However, in the second case, we see the third target on the right, but not so good the one in the middle. So this also depends on what kind of target we want to illuminate, what we want to perceive, how reflective it is. However, what you should take with you is that when we have automotive and road lighting together, there is an effect that luminance differences vanish, and as a result, objects or potential hazards for the driver are rendered invisible. And depending on where the target is, further away from the car, what kind of road lighting there is, how reflective the target is, there's a transition between positive and negative contrast, and this has to be taken into account. And what I really want to put emphasis on is that additional headlamp light can actually deteriorate the visibility conditions, resulting in weaker and less road safety. And such that we need for different road lighting scenarios different headlamp light distributions. Today we are only going to talk about the different road lighting. However, if you're interested in how I recommend to illuminate the scene from a car perspective, I can only point to our recent publication hella2, which you can find there, and there I precisely describe what I would recommend for those light distributions. However, today we are talking about different road lighting. And for that I brought you 6 different pictures, which I took in Lippstadt, which show typical road lighting sceneries, and you can see there, or maybe also you can guess from your own experience, that road lighting is quite different. You have very powerful installations, like on the bottom left, for example, where there's a very high road surface luminance created by the road luminaires, or you have some dark scenarios, like on the bottom right. And in addition to that, it's not just about the brightness itself, but also about the uniformity. For example, on the top right, you can see that there are plenty of dark spots between the road luminaires. So it's not so easy to put all those things into consideration. So luckily there is a European standard for road lighting, the 13201, which has pretty much 3 different parameters. The average luminance on the road surface, which is determined in an evaluation area. You can see it on the right, 60 meters ahead of the car in a square with a width equal to the street width and a length or depth equal to the distance between 2 road luminaires, and there the average luminance has to meet some required values. In addition to that, it's also considering the uniformity of light distribution of the road lighting. So we're also measuring in this evaluation area the ratio of the lowest luminance and the average luminance, and we also have to meet some requirements there. And finally, since we are adding more light sources to the scenery, there also has to be a limitation of the glare induced by the road luminaires to the driver, so this is also taken into account. And what the road lighting standard offers are those 6 different classes. M1, which is the most powerful one, to M6. They are designed for streets where there is where mainly motorized vehicles are the main road users. And you can see that regarding the uniformity, which is the 3rd column, there's not so much of a difference in the values. Same goes for the 4th column, the threshold increment factor, which is describing the increase of glare coming from the road lighting. However, the average luminance, which has to be met to be in one of those classes, varies quite a lot in steps of around 0.1 candela per meter squared. This is the order of magnitude of the differences. So there we can differentiate. So according to this, now we have to think, when we want to adapt the automotive headlamp to the road lighting, how do we know what road lighting is present there? And there are several approaches. For example, we could realize a direct communication V2I to the road lighting itself. Road lighting is getting smarter, it's going to be part of a smart city environment, and such that it could tell us what kind of road lighting class it is, how much light it's emitting onto the road, and then we can use this information from a car's perspective. However, since road lighting is typically bought by cities and counties, they are quite cost efficient, so there's not so much smart functionality in the road lighting yet, even though it would be technologically possible. Another approach would be to have a database in the cloud where, depending on in which position I am, there is information about the present road lighting. However, this database someone has to set up. It has to be up to date, because otherwise we get wrong data, and in consequence we could have too few light coming from the car. So this is why we chose option number 3, which is the use of an automotive sensor to classify road lighting pretty much by measuring the luminance of the road surface according to the standard. With this, we also have really live data, which is happening right now in front of a car. We are not depending on any technological development of the road lighting or that the database is up to date, but actually we see what is there right now, and we also take into consideration, for example, how the road surface is when it decreases over time. Then maybe the class of the road lighting is changing as well, so this is the way to go. As a consequence, some research questions came up. The first one is, can we use a conventional camera to do this, to measure the road surface luminance, and if so, what kind of measurement error can we expect? And if we know that we are able to measure it, what is the consequence when we want to apply it during driving? Does it work? What are the new challenges coming up there? And I try to answer those questions today. And the approach we did to find the answers to those questions are that we pretty much have two different steps: the characterization of the camera we used, and then the application in the field to see if it really works. And for that, we first characterized the camera with its different color channels. Now we combined them in order to somewhat measure the luminance, which we then can later on measure in the field and then follow the classification of the road lighting. The camera system we used was a Bowmer VCXU23C with a 1/1.2 inch sensor format. It was a CMOS sensor in there by Sony. The resolution was 2.3 megapixels. We used the RGB biofilter because we need the color information, and exposure times were quite a range from 27 microseconds to 60 seconds, and we used this system to have as many degrees of freedom for our research. And so while we did some more characterization than I'm going to show you today, we only focus on the spectral sensitivity and how we can match this to the spectral sensitivity of a human. And for that, a short recap for you: the luminous efficiency function you can see here on the left is the spectral sensitivity of the human eye. It has its peak at 555 nanometers when we're talking about photopic environments. This is what we typically assume when doing automotive lighting research. And then it symmetrically decreases for lower and higher wavelengths. On the right, you also see the definition of an F1 prime mismatch index, which is a term that describes the deviation of a system we have with a specific sensitivity to this sensitivity you see here. And while the equation is not that easy, it basically shows how much, when integrating, how much difference in area underneath the two sensitivities have. So first thing was to actually characterize the different color channels of the camera, and for this we integrated it, we put it into an integrating sphere. As a result, we could be sure that all the light we emit into it really hits the camera we want to investigate on. For that, we used a tunable light source, such that we can really scan through the spectrum we want to have information about, and it has a 5 nanometer bandwidth. After having it corrected by the spectral radiant power of our light source, we got those results you can see on the left. You can see the red, the green, and the blue channel, and also the human sensitivity we want to match. And you see that, of course, there's quite a distinctive difference between the three different channels. They are shifted to lower or higher wavelengths. This is why they have a color. And you also see that none of them is really perfectly fitting to the human sensitivity. Especially the blue one, for example, is quite bad. So we have to find a solution to that we can try to model with the given sensitivities the spectral sensitivity of the human. And for that, we used the polynomial approach, which you can see here. The idea was to combine the red and the green channel. You see the blue channel was already discarded because it was not really that helping in this situation. And then we did an optimization where we tried to minimize the F1 prime mismatch index I introduced to you before. And according to that, we determined our terms in this equation you can see there. And actually we went as low as 21% F1 prime mismatch index. So is it good or is it bad? If you think about calibrated luminance measuring video photometers, they come around 5%. So of course there is an offset in there, because also they are much more expensive, and our system is not so expensive, and it's not built up for that. So we have some deviation, but it's not that big of a thing here. However, we also see that, for example, at 569 nanometers, you can see that here on the left, where the turquoise or teal graph, which is pretty much the equation you can see on the top right. You can see that at 569 nanometers there is a wider difference of 26%, and we should have this into account when discussing the results later on. The next step was now to combine the values of the camera with luminance values we want to determine. And for that, we measured different luminance values with a calibrated measuring video photometer and also with our camera system, and then we combined those measured luminances with the pixel values we determined, and we did this for different settings of our camera with different exposure times and different gains. And you can see some results here on the left. You see that for higher luminances our pixel values are increasing, and depending on what kind of range, what range of luminance we want to measure, we need specific settings, specific gains and specific exposure times. And also we want to have this slope of our graph on the left as high as possible, because then we can differentiate better between different luminance values. And yeah, this is what we would expect before, and this is what we did before going then into the field. However, not really into the field yet, because we first wanted to investigate what influence different light sources with different spectral distributions had. And for that we illuminated 8 different targets, you can see here on the left, which have different reflectances. As a result, we got different luminances we measured, and we illuminated them with 4 different headlamp types, a halogen, a xenon, and 2 different LED systems, just to have some information about how repetitive it is for different LED sources. And we then determined the same thing again with the calibrated video photometer, and then compared those results. And as you can see, the average error over all those different luminances we had there was below 15%. You can see that it depended slightly on what kind of headlamp we used. For example, for the halogen and the xenon, it was not that high of error, it was around 5%. However, when having LED headlamps, there is some increase in the error. This is due to the fact that at 569, where the phosphorus part of the LED is also emitting light, our sensitivity is not matching that good to the luminous efficiency function. However, when we are aware of what kind of light source we use, we want to measure, then we can determine some correction factors. You can see here in column 3. And when we correct our results with those factors, we get a corrected error, and then it's below 10%. So having discussed the influence of different light sources, the next step was then to go into a static scenario to determine, can we classify road lighting? For that we did this in 3 different scenarios. You can see on the bottom left, they varied in their luminance. The scenario number 1 had the lowest luminance, and scenario number 3 had the highest one. And let me show you the results for those measurements there. In scenario 1 and 3 we use different headlamp light distributions. The first one is off, that's a very simple one, where we just turn off a headlamp and only measure the road lighting. Then we use only a pre-field illumination, and then finally we also use the conventional low beam. And what you can see here in the graph, in blue you can see the actually measured luminance using the calibrated system, and in red you can see the results of our camera under test. And you can see that there is some deviation of the measured luminance values. However, I gave you the errors for that, and they are overall below 0.05 candela per meter square, or 12% you can say. And think about what kind of steps we had between the different classifications. They were 1 order of magnitude higher, so we can estimate from that result that we are quite good at measuring the road surface luminance we need to classifying the road lighting. What we also see here is that the light function itself does not really have any influence, because it's just not illuminating the area 60 meters ahead of the car, only slightly, maybe the low beam, but overall this is independent from that. So having discussed the static scenario, the next challenge was the dynamic scenario, and there are some problems occurring. For example, when we are driving, the inclination of the car changes. The tilt is going up and down depending if we are accelerating or braking, and as a result the pixels in our measurement do not correspond always to the evaluation area. Instead we have to determine which pixel belong to that area pretty much in every step for every inclination of the car, and this is quite difficult. The next step is also close to that. When we are not going a straight road, when there is a turn to the left or to the right, and there is no area 60 meters ahead of the car where we can measure the road luminance. as a result, we would measure something, bushes or buildings or something like that, so we also have to take this into account that we measure to the left or to the right, for example. And another problem, which is also shown here exemplarily, when there are other traffic participants, they can be either inside the evaluation area, then they might alternate the road surface luminance to higher or lower levels, depending on what kind of traffic participants they are. And what you can see on the right, when there are other cars passing by, they also illuminate with their own headlamps this evaluation area, and as a result, the luminance in there increases. So pretty much the solution for all those three different challenges is only additional image processing. And luckily there is already a lot of image processing going on in the sensors in the car, so this has to be implemented pretty much. We are aware of where other traffic participants are as a result of the increased development of automated driving. We have very well awareness what is around us, and when we set up this image processing, we can overcome those different challenges. So let me conclude. We showed that we were able to classify the road lighting according to the European standard 13201, and we did this with a maximum error of 0.05 kernel per meter square, which equals to an average relative error of 5.7%. We also showed that there is some influence of different headlamp functions and different light sources with different spectra. However, overall for our application it was neglectable. Coming back to the beginning, so we need some kind of system of this kind to have fully adaptive light distributions for road lighting, so it's a key component for that. However, before having it really when driving, we have to overcome the challenges I